Sorry?
And your pen succeed.
Yes, I come with a bang. I have unlimited resources. Okay, well, thank you very much to the organizers for inviting me, and I don't know if I really belong here. I don't know if you will find this interesting. It's not about quantum, and it's not directly about linguistics. It's about just lattices. So it's about lattices, but and duality. But it is actually work I have used in the past together with Alessandra and Mike Dunn to give relational semantics for substructural logics. And also recently there are some people here in Oxford who are actually interested in this. So this is why I thought this is the most useful thing I could talk about. So the first part of my talk will just be about finite lattices. So I'm not going to keep saying finite, finite, finite until I say I'm in part 2, it's all finite. Okay? And I want to understand how do we get representation of finite lattices. So what's the basic idea behind it? It's the same as when you decompose natural numbers into primes. Right? So the idea is if you have an arbitrary element of a lattice, you can see whether it can be decomposed into a join of two smaller elements. And of course, because the thing is finite, you have a descending chain condition and it terminates, and so you get everything as a join of join irreducible. So the definition is X in a lattice L is join irreducible if and only if whenever it is equal to a join, then it's actually equal to one of the elements. Right? And then you can say then the basic observation I just gave is that in the finite setting, every element in a finite lattice L is a join of join irreducibles. Okay, the set of all join irreducibles I will denote J of L. And this is a subset of L. Let me see, what do I want to say first? So, the fact that every element is a join of join irreducibles tells us that we have an embedding for any finite lattice L of it into the downsets of its set of join irreducible elements, right? You just send every element of the lattice to the join irreducible elements that are below it. And that will certainly give it as a join from the argument I just gave. Now, it's also pretty easy to see that if you take the mean of two elements, then which join irreducibles are below? Well, just the ones that are below both. So this is actually a mean semilattice embedding. And maybe I do an example. So if I have something like I will choose a non-distributive lattice, so here's N5. What are the join irreducible elements? So they're essentially the things within degree 1 from below, right? You can't write them properly as a join of two things. So it'll be this element here, and this element here, and this element here. This one not, it has in degree 0, it's the join of the empty set, and it doesn't belong to the empty set, and this one is join of these two. So it's also not join irreducible. So the set of join irreducible elements is a chain together with a single point. It's this poset. Right, and the downsets of that is what? Well, so you'll have the empty set, and you'll have that singleton, and you'll have that singleton. And then if you have this one, you have to also have this one. And then you might have just these two, or you might have all three of them, right? And so you get this lattice. This is the lattice of downsets of the joint reducibles of this N5. And of course, how does this embed in there? The bottom corresponds to the empty set. This element just becomes its down set. This element here, and everything is of course up here. And you can see it's a meet semi-lattice embedding, but it's obviously not a joint semi-lattice embedding. So this doesn't work in general. If I started with this lattice here, and I took its joint reducibles, what would I get? I would get again the same set, right? And in fact, that one, to take the down sets, you of course get this. And in fact, what is the thing? You will get, this map here will be, eta is a surjection if and only if L is distributive, if and only if joint prime and joint reducible is the same. Maybe I don't say that, but so anyway, this is actually the basis of this duality that Sam was talking about in the infinite case, and it's what is called Birkhoff duality for the distributive lattices, but it actually works for lattices in general, except you only get an embedding. Okay, so what can we do for not necessarily distributive lattices? Well, one observation to make is that we could actually, instead of having used joint reducibles, we could have used media reducibles, right? The same argument works, just the other way around. So could have used media reducibles, and we'd get pretty much the same kind of theorem. Unfortunately, we would also get the same thing as this. It would only be onto if it's distributive. But, let's see, so what actually happens in the distributive case is that let's look at a picture. If we have a distributive lattice, and we have an element x which is joint reducible, then if we take all the elements that are not above it, so the complement of its upset, so these guys over here, and we take their join, so the join of all the elements in the lattice so that the x is not below A, where will that be? Can that end up here? Well, that's exactly what distributivity says it can't, right? Because we'll have that if x is less than this join, then x meet this join of these A's would be x. And so then if we have distributivity, this is x meet A, x not less than equal to x. And this is now a join that gives x. So if x is joint irreducible, this is not possible unless one of them is equal. If one of them is equal, that means x meet A is equal to x. That means that A is above x. And there we specifically said they were not, right? So this actually gives the largest element in the complement of the upset. That means that actually x and this twin element, they actually split the lattice in disjoint pieces. So, and this one is of course uniquely determined by x, usually call it kappa x, and that's a media reducible. Okay, so meet and joint reducibles in a distributive lattice come in pairs, in twin pairs that split the lattice. And so actually in the distributive set, not only would we get something like this, we would get exactly the same, because the set, this kappa is actually isomorphism between the set of media reducibles and the set of joint irreducibles. Is there something to erase with somewhere?
Yeah, on the board.
Oh, there. So, whereas if you have a non-distributive lattice, something quite different happens. Kind of to give you an extreme case, consider a finite lattice made in the following way. Start with a tree that branches at least twice at each stage. That's enough. Okay, and then just add a bottom. Okay, so a tree with a bottom added. So make a lattice. That looks weird. Okay, anyway, that's a bottom and that's a tree. But if you make a lattice like that, then what are the joint irreducibles? What are the things within degree from below equal to 1? It's just exactly these guys, right? Because all the other guys, since I had branching, there will be non-trivial joins. So my joint irreducibles of this lattice are exactly the leaves of the tree and nothing else. And what are the mean irreducibles of this lattice? Well, that's all the ones within degree 1 from above. That's everything in a tree. And obviously not this bottom, because there's a bunch of things. So, except the top is not, right? So it's actually the whole tree minus the root. So there are many, many more mean irreducibles than joint irreducibles. Okay, so in the non-distributive case, these two things really give very different embeddings into different things. And the secret of giving representations for lattices is actually to keep both. And then you are in fine shape. So we define for a lattice L a polarity that is two sets and a relation between them, which I'll call order, even though it doesn't really make sense because it's between two different sets. Where X is the set of joint irreducibles of L, Y is the set of mean irreducibles of L, and I forget their order on themselves, but just remember only the order from X to Y. So this thing I'm calling order is actually just the order from L, but restricted to X cross Y. So for example, if I have something like M3, then these middle points are both joint and mean irreducible. So X is equal to Y, so it's really just two copies like this. Y is the mean irreducibles, X is the joint irreducibles. And the order between them is how they're related in here, and it's of course that element is that element, so they're related like this, and like this, right? And the point is, anytime you have such a triple, of course you get a Galois connection. This is essentially a polarity, and so you can look at the Galois connection, which here I'll call upper and lower, because I'm thinking of this kind of like an order. So I can go from the power set of X to the power set of Y and back, just by taking all the points that are above all the points in a set, you know, just to, so here from a set of A's I take the set of all things in Y, so that for every X, if X is in A, then X is less than or equal to Y. Right, so all the common upper bounds of the set A and all the common lower bounds of a set B, that's the map in the other direction. That's the Galois connection associated with this polarity. And the Galois closed sets of this polarity is exactly isomorphic to L. Okay, so in other words, this will be contained, the Galois closed sets will be contained in the down sets of this one, and in the the upsets of this one, but the intersection will be meet, so it will be essentially this map for intersection, but you don't know how to do union, and how do you find out how to do union? By also remembering the stuff about the mean irreducibles. That's essentially what's going on. Okay, so just to see the distributive distributive case, how does that sit inside there? So in the distributive case, remember we had an isomorphism between the joint irreducibles and the media reducibles. So actually x is isomorphic to y through this kappa. And to say that a joint irreducible is less than a media reducible, which is some kappa of some y, well, this exactly meant that we have y and kappa of y. So for x to be here is equivalent to saying that x is not there. So this is actually the same as saying that y is not less than or equal to x. Right? So the polarity you get from a distributive lattice is actually of x are the joint irreducibles. Y is essentially just another copy of x. And what does it mean that an element in this copy is less than an element in this? It just means the order negated upside down. Okay? So a polarity that's of this form is a special one of those, and those are the ones that exactly give distributive lattices. In other words, so L gives this polarity if L is, or D, let's call it, if it's a distributive lattice. And then we get that D is isomorphic to the Galois closed sets of this thing. Which of course is also, we know it already is isomorphic to the down sets of just X as an ordered set. So essentially this is a generalization of down set, okay, for these special polarities. And the Boolean case is even more special, of course. What is a joint reducible of a Boolean algebra is just its atoms. And what are the media reducibles of a Boolean algebra? Just its co-atoms. And of course the atoms and co-atoms of a Boolean algebra are related by complementation. Right? That's the kappa in that case. And so there you get that the order is, that is x, is less than or equal to not some atom y. X is below the complement of an atom, if and only if that atom is not x itself. Right, that's clear. So it's just this. So the special case of these polarities that give Boolean algebras are the ones where you have x and not less than or equal to for any set. Right, so the category of sets fits inside this category simply as these objects. Po-sets as these objects. And okay, the general ones are x's and y's and less than or equal to 2's. How am I doing? Okay. So here I've said which ones correspond to distributive lattices. They come from Po-sets and they're built like this. The ones that correspond to sets or Boolean algebra, complete Boolean algebras are the ones you get by taking x and not equal. I haven't really told you which polarities I get here. So what are the characterizing properties of these polarities I get by doing this? So starting from a lattice and doing this. And essentially it's two properties, so it's a separatedness, which essentially just means that if you take any two elements of the set X, and you look at what media reducibles are above them, so you look at, well, so if X is different from X prime, then the upset of X is also different from the upset of X prime. In other words, every element is given by which media reducibles are above them. Okay, so that's also clear, because in a finite lattice everything is a media reducible and a joint of joint reducibles. So they have to be, you can't tell them apart with these things. And of course, the other way around. So that's separated, and the other thing is that it is reduced. And so what does this mean? Here for this it's good to have a definition to make it a little bit simpler to understand. As we can actually induce an order on X from this polarity, namely just by saying X is less than or equal to X prime. So that's not the same relation as that one, it's in a sense an extension of it to X itself. Okay, so the definition of this. If and only if the upset of X, which is defined by this order, that is all the elements of Y in the relation with X, this is bigger than the corresponding thing for X prime. Okay? Just, there are more media reducibles above X than above X prime, right? Which says that X is lower down. So if we define that, then this property says the following. For every joiner reducible, there exists a media reducible, so that X is not below Y, okay? But for every X prime, which is strictly below X, X prime is below this Y. So what does this say? Some X prime being strictly below X, that means that there actually is some Y prime which is above X prime but not above X. And this is just moving the existential quantifier outside the universal one, right? So it's saying there's a choice of Y which does it for all the X primes at one time. Okay, and that's essentially like saying that X acts like an atom or like a joint reducible. Okay, it says X is a strict jump in information above the X primes that are below it, that are strictly below it. So this is exactly the thing that makes it act like atomic or a downset lattice. And of course we need the dual things. For every Y there exists the X, and just imagine the dual. Okay. So if you take these kind of frames, so actually I told you everything was finite, but right now it doesn't need to be finite. If you take these frames, so I'll call these RS frames. And from any RS frame, using Galois connection, so here the generalization of power set is Galois closed sets. Then I get a lattice. In general, it will be something we'll call a perfect lattice. And if I have a perfect lattice, then I can take its joiner reducibles and its media reducible and the order between them. And this is a duality, a discrete duality like the one Sam was talking about. In fact, in here sits as a special case the posets, which were the ones I gave a minute ago, and they of course are in a duality with these doubly algebraic distributive lattices that Sam talked about, which are a special case of these. And in here sit sets as a special case. And if you take this exact duality, it specializes to this. And here are covers. Okay, so this is a generalization of the duality between sets and covers, but for non-distributive lattices. Okay? Okay, so now here actually it's not finite anymore. So maybe I should say part 2. Okay, so my sets don't need to be finite, and then this is why I have to say something here, because in general, for non-finite lattices, say if you have something like this, infinite, so n upside down cross n upside down with a bottom added. This lattice here has no join irreducibles. You can just look, every element is a join of some things below it, right? So obviously you are not going to be able to do this. Even worse, say if you take the Boolean algebra you get from classical propositional logic over countably many generators, you probably all know it has no atoms, right? And so of course it doesn't have any coatoms either, right? So in this case, the join irreducibles as well as the meet irreducibles is an empty set. So for infinite lattices you cannot do this in general, but what you can do is you can use Sum's magic of canonical extension, and then you can always embed an arbitrary lattice. So for any lattice L, you can embed it in some completion of it, which we call L delta, in such a way, and this embedding is such that this thing becomes perfect. That is, and what do we mean by perfect? So this was actually Tarski and Jansson that came up with this name. So perfect, well they had it for Boolean algebra, so the perfect for them was covers. And this is just the lattice version of perfect. So here perfect means complete and join generated by completely join irreducibles and meet generated by completely meet irreducibles. So enough join irreducibles and enough meet irreducibles. Okay, and as soon as you have that, then this whole story works. Okay, so then it's just like the finite case. So this duality, that's also why actually this is not finite, right? This works in general. And then the way this has interest in a broader sense is because you can always embed any lattice in a very natural way in one that is like this. Okay? And this is in fact the scheme for getting completeness theorems, just like Sam was talking about in the distributive case, for arbitrary, for logics even in the non-distributive setting. So, but now the generalization of set is this RS frame. You know, I say this is a duality and I haven't said a word about morphisms, so that's a bit unfair. Let me just say, of course over here on the lattice side, morphisms are just complete homomorphisms, right? And so the question is, what's the dual notion of complete homomorphism? And essentially what the question is if you have a complete homomorphism from one lattice to another, then as you all know, if you have complete lattices and complete lattice homomorphism, that means it preserves both joins and meet. So it has both a lower adjoint, which we call H flat, and an upper adjoint, H sharp. Okay? And so the question is, how can we understand these dually? So this is a place where it's much nicer, say, in the distributive case. Because what, so, question? In a sense, see, in duality, if you want to find the dual of a homomorphism, it's essentially its adjoint. That's the dual map. Okay, either the upper or lower, depending whether you take join reducibles or meet reducibles. So the question is, how can you feel on the lower adjoint? How can you tell on a map H, which has an upper adjoint, that its upper adjoint has itself an upper adjoint? Right? I mean, if you have a map, then it uniquely determines its upper adjoint. Then you can ask, does this upper adjoint happen to itself have an upper adjoint? That should be able to, you can tell that for already down here, right? And so the point is, in the distributive case, in the distributive as well as in the surjective case in general, so that is either distributive or surjective, then you're in business. then the answer is if and only if this lower adjoint sends join reducibles to join reducibles. Okay, and so therefore you can then define the dual of a homomorphism is just the lower adjoint of it restricted to join reducibles. Okay, that's in fact in Priestley or Stone duality, this is the way it comes about. Okay, or Birkhoff duality. Now in the more general lattice setting, if you don't have surjectivity, this is not quite true. And then actually the notion of morphism splits into a pair of relations. Okay, so it gets more complicated. Dual of H is a pair of relations. And using Sahlqvist type stuff from modal logic, Alessandro and I at least figured out what it was in about 15 minutes over lunch, whereas actually for duality for lattices was first invented by Urquhart in '68. And until now there have only been dualities for surjective operations. Okay, I think until 80, 90, beginning of 90s. Okay, so it took many years to have any idea what the dual was, but really with this point of view of how this generalizes from the Boolean algebra setting, it's quite easy to see how to get them. It's a bit more nasty, so I won't tell you. But you have a notion of morphism, and it's clear what it is. So it's a kind of generalization of critical relations. Okay, so what I wanted to say now, do I still have a few seconds?
5 minutes.
5 minutes. So then I wanted to say what this has to do with relational semantics. And in particular I wanted to say a few things about this Lambek-Grishin calculus and oops, that wasn't mine to erase. So what does this have to do with relational semantics? So the idea is essentially this. If you have a logic that is given syntactically, then in many cases it corresponds quite easily to to some kind of algebras. So some class of algebras, right? Like say partially ordered monoids or Boolean algebras, or depending what modal algebras, so on. So you have some easy translation into algebraic language. Then now, using canonical extension, you can take the canonical extension of all these algebras. They are ones in which these embed all, and which and that are perfect ones, right? They fall in this perfect lattice duality. So this is some class of perfect algebras. And these perfect algebras, as we saw, are in a discrete duality with some kind of frames. Actually, the RS frame part is just for the lattice part, but in general we'll have additional operations. So here we'll get RS frames with additional relations. But just in a completely standard way applying this duality. Okay, so you just follow your nose, at least if you've gotten here from the logic. You take the canonical extension, you take the duals with this discrete duality, and you have a concept of Kripke frame. And what does it take to have completeness? Well, if whatever notion of deduction you have here ends up meaning that you have some equation or inequation here, then these inequations lift to the canonical extension. So when you do canonical extension to the operations and everything, and you get a version of it up in these algebras, you'd want to know that this holding implies that this holds. And this is what is called canonicity. So this is one thing you have to prove, that they lift to the completion. But if you have that, then after that you just have to translate what this means to here. And that's usually called correspondence. Just translating what this property on the Galois closed sets corresponds to over here on the RS frames. And then you get a class of frames with this property, and that will give you complete semantics, you know, always just in this format. And the point is now if you add a bunch of different properties here, you just do it for each one of them and it's completely modular. Okay, so in this way, now I'm probably completely out of time. For the Lambek calculus, what do you have? So you have essentially a partially ordered set with a family of residuated operations. Well, this, it might even be a lattice or not, but actually there is a canonical extension even for pose sets, and so this will give you an RS frame for this part. And then from this, these are all residuated. So like Sam told you, they actually all come from one ternary operation. So you get things like this, with this R has to be compatible with this. Essentially that means that if you fix any two coordinates, and you look at all the things in the third one, this has to be Galois closed. And for all coordinates, okay? So that's the compatibility. And then now you can start adding, well, what do I want? So this would be non-associative Lambek calculus. Here's your complete semantics. Now you say, oh, I want it associative. Well, then you can actually show that associativity up on the full algebra corresponds to just having associativity on elements in X. You know, that this is the same whether you bracket like this or like this. And this easily translates to first order property. It's commutative, you find a different first order property. The relations, if you have weakening, you get another one. If you have contraction, you get another one, and so on. And this is all completely modular. You can add whatever you want, and you get the corresponding cryptic semantics. Now, if you have Lambek-Grishin, then you have another family, namely this. So now let me call this one like this. Then you also have this plus family. And this is just completely dual to this, so then you get not only an R, but also an S. It's also ternary, and with the dual properties of this one. And then if you have interaction, then you get something, then this works also. So maybe as the very last thing, I just show you something, because I think this is strange and interesting. Let's see. Michael had something like 8 times. He actually didn't, he gave them as rules rather than as axioms, but let me write it like this. It's actually like a bracketing of something from the one family with something from the other family. So, so it is a strange kind of associativity where you have really completely different operations. So this is one of his interaction axioms? No?
No, the C goes with the A and the B stays out.
Oh, of course. I put them in a different order.
Yeah.
Sorry, that was not my intention.
Okay.
Yeah, like this, right? Now let's see. This guy here, what kind of operation is this? This is one with upper adjoints, right? So this is actually a kind of diamond. This one is the lower adjoint of the plus, which is kind of like a box. So this is actually also a diamond, but with a flip in the second coordinate, with an order flip in the second coordinate. So a completely join preserving operation should do what? You need to know what it does on join reducibles, right? So this is why this spot is kind of natural for elements from X. This spot also, since it's the positive spot of this other diamond, should really also be interpreted as an X, different X. This one is flipped, so it should be interpreted as a Y. And actually the typing of X and Y still is, works in the other way of bracketing. So this makes sense, and what actually happens is that this holding for all A, B, and C second order variables, so this is like Galois closed sets, or in other words, elements of the original infinite lattice. This ends up corresponding to having for X and X prime in X, and Y in Y, so this is now over on the dual structure, having the corresponding thing for these elements. Okay? And strangely, if you use one of your other equivalent, they come in quartets, as you say. The other quartets will use, say, 2 Ys and 1 X. Then you plug in Ys and X's, and it's actually equivalent. Okay, so the way to translate is just plug in the obvious kind of elements, and there you have it. Okay, so and so this gives, we saw in Michael's talk and in the talk right afterwards, if you just have a Lambek-Grishin, then you can do Kripke-style semantics. If you also have a lattice operations, then you were doing something like what is it called? Phase spaces. But the point here is it's the same semantics throughout. You can add whatever you like, all the way up to Boolean, and it keeps being the same. Okay, so that a strange thing also about this is it seems to say that maybe you should be able to think of these operations as actually as X being closed under them and Y being closed under them. And this is what you have, say, in these things Manouche and Prakash are looking at, and so on. So that's I find a very interesting question, whether you can actually, without lots of generality, think of these not as relations on X and Y, but as operations on X and Y. But this I don't know. Okay, thank you very much.
It's time for one short question. Okay.
So how fine-grained can you do these dualities? Could you also get something from modular lattices?
It is also for modular lattices, but characterize modularity.
Yeah.
You know, modular long, if you think about it, interestingly enough, Hilary and I looked at this a few years ago, it's like a whole family of McKinsey axioms. Okay? So you can, but I expect it may not be canonical. Okay? Because it's the McKinsey axiom. It's like a box diamond, less than diamond box. I cannot remember the modular long by heart, in my head, but it's like if you read it, you will see it's like a family of McKinsey axioms. So I think it's a very interesting question, but I don't know the answer.
Okay, I think we have to switch to the next speaker. Thanks for the final talk in this slot.